Welcome to the APL quest. See APL Wiki for details. Today's quest is the 9th from the 2014 round of the APL problem solving competition. We are computing how far an object reaches based on the angle at which it is thrown and how fast it is being thrown. Now that doesn't actually matter because we are given the formula ready to use. All we need to do is translate that to APL. So the distance is, well, we use 9.8 we're given as the gravitational constant, so we need to divide by that eventually. It's the square of the velocity times the sine of 2 times, and then we need the angle, but it needs to be in radians for sine to work correctly, and we're giving it in degrees, so we just need to translate that. So we multiply by pi and divide by 180. Now, we can simplify this a little bit. I like to get rid of parentheses, and multiplying by a square of a number is the same thing as multiplying by that number itself. We're multiplying by 2 over here, and we're dividing by 180, and there's no need to do both. We can just divide by 90 instead. That makes it look kind of nice with the 2 circles. Some test velocities and some test angles. This doesn't give us quite 0 for the 90 degrees angle, but that's due to floating point inaccuracies. Of course, if you throw something straight up, then it comes straight down and it didn't move from the origin at all. So this is very simple. To spice this up, somebody came up with a challenge of doing this without the circle function. We're using circle function twice here. For the sine, 1 circle, and for multiplying by pi, just magnetic circle. And it's a bit more of a challenge to do it without circle. But we have some ways we can do this. First, let's do the sine. So we can use a Taylor series for the sine function. That's the alternating sum. And then we start off with the odd numbers. We don't even need very many terms before we get a very accurate result. And then on those odd numbers, we raise the argument to those odd numbers and divide them by the factorial of those odd numbers. And then the alternating sum of that should give us a correct result. Let's try this out. And compare with the native sine. That looks very accurate indeed. Okay, so we've solved that part. Now, as for pi. So for pi, we could start with Euler's identity. That's in the APL, 0 is equal to 1 plus, and then we need e to the power of, that's the exponent, just magnetic power, and then pi times the imaginary unit. So this holds, and we need to break out the circle from here, so to say. Well, let's start by removing that, so subtracting 1 on both sides of the equality. And then we have a e to the power of, so we can change that by removing, we can get rid of that by taking the logarithm on both sides, so that cancel each other out. And we just need to take the logarithm on the left. Now we have pi times the imaginary unit. So if we multiply by the imaginary unit again, then we get -1. And then we can multiply by that over here. And then we just need to negate. And we can, for example, do that by negating this over here. So now we've broken out pi, and that means we can just assign this And you might consider this a little bit of cheating because the built-in constant pi is, of course, hidden inside this formula, inside the whole arithmetic implementation of logarithm with negative numbers and dealing with complex numbers. So how about using a series instead? And then we have some might have a series, and the very simplest of those is not very accurate, but it's very simple. It computes a quarter of pi, so we multiply by 4. It's the alternating sum simply of the reciprocals of negative numbers beginning with 1. And even if we take, say, 1,000 of those, it doesn't give a very good result. I mean, it looks kind of okay, but if we compare it with the actual value of pi, we can see that it's quite a bit off. There's a little bit more complicated formula, which is much better, converges much faster. And here we are computing pi divided by the square root of 12. So we start off by multiplying by the square root of 12 to get actual pi. Again, it is an alternating sum of reciprocals. This time we have to start with 0, and then we just do natural numbers, and 100 is actually enough. Even much less than that would be enough. For each one of these, we take 3 and raise it to that power, and multiply it by the incremented 2 times that number. Now 2 times the number, same thing as adding it to itself. So this is 1 plus 2 times k, and then times 3 to the power of k. And this looks really good. If we compare it to the number that's built in, then it says it's equal. And if we try to subtract them to see what is the actual difference, within the floating point accuracy that we have here, 64-bit floats, then they're actually equal. So that's very nice. Now we have signed that, and that means that we could substitute these into our formula. So 9.8 divided by alpha times the sine of pi times the argument divided by 90. Of course, we could compute that constant of pi divided by 90, but it doesn't really matter. And then we can try. We need to use an each here because we're using a series computation. Oh, well, this was the wrong one. This is D, but it doesn't matter. And then E is the new one. And we can see that we get pretty good values for the numbers that are 0 or far away from 0, and a good enough value, even for the one that's supposed to be 0. Thank you for watching.